So here is so in the previous session we found values. We found matrix representations of Lx hat and Ly hat, and here we show that those matrices obey the same kind of commutation relations, have the same kind of commutator result as the operators directly. Okay, and here's proof. It's fairly straightforward. Just basically just boils down to matrix multiplication. It's pretty easy. Okay, so for here, now if I put a hat over these, the result would be IHLZ hat, right? If you're talking operators, but now we're talking about matrix representations. So now we're dealing with matrices that have equivalent behaviors as the operators. That's why they're called representatives, if you like, representations of the operators. So so here's the commutator of the matrices. So Lx Ly minus Ly Lx. Okay, that's the definition of the commutator. So here's your Lx. Where does this term come from? Well, Lx is actually h bar over square root of 2 something, the matrix. So you square, so you get h bar squared over 2. And here's your matrix for the Lx, that's your Ly. And now the other way around, Ly, Lx. Okay, now it's just matrix multiplication. Subtract this result from that one, you'll get this. And you will recognize this from 2 sessions back. That's the matrix that corresponds to the operator Lz hat. Okay? So you can just rewrite as Lz. So this is now the matrix representation of Lz hat, the operator. Okay. Now other commutation relations. Now L squared. Now previous session we found the matrix corresponding to L hat squared, and now L squared. The matrix for L squared is diagonal. Okay, and the matrix for Lz. The z component of the L operator hat, Lz hat. Both of these matrices are diagonal, and then if you multiply the commutator of those two diagonal matrices will of course be 0, right? Because that's just the nature of diagonal matrices. Okay, so of course these two commute. Now the operators commute, and now we've just shown that the corresponding matrices also commute, right? So they have the two sets, like the operators and the corresponding matrices, the representations of the operators, the matrix representation of the operators. They obey the same rules. They have the same algebra, if you like. The commutation relations are the same, or the equivalent. Okay. Now, we can form, and I've said this a few times before, but it's possible, for a given L, your M can have 2L plus 1 different values, ranging from -L, ... 0 ... L. So there'll be 2L plus 1 different values of M for a given L. All right. So that means, let's say L equals 2. So we have an angular momentum of 2. The L times L plus 1, that's the eigenvalue, well, h bar squared. That's the eigenvalue, the allowed eigenvalues for the angular momentum. So L can go as high as you like. You can have very high angular momentum quantized. But the point is, since L are integers, the L times L plus 1, they give discrete, quantized values for the allowed angular momentum in quantum mechanics. Now, since M ranges over 2L plus 1, if we have, say, well, effectively we can have an infinite number of matrix representations of an angular momentum operator, right? Because we just choose an L that we want, and then the matrix representation of that operator for large L will be a large matrix, a square matrix of size 2L plus 1 squared. Okay? So, for example, say, now here we've been talking matrices 3 by 3, which is the simplest case when L is 1. Okay? And so M ranges over, well, M will have 2 times 1 plus 1, hence 3. So the matrix representation is of size 3 by 3. Okay? But if L is 2, then M can range over 5 different values, minus 2, minus 1, 0, plus 1, plus 2. So the matrices, the matrix representation will now be a 5 by 5 matrix. And to calculate what that matrix is, you'll go back to the, now I don't think you can see it actually, but the previous session you had an overlap integral. I'll just read it out. So integral YLM star operator, L squared or LZ times Y L M dashed, and then sine theta d theta d phi. Okay, so you can calculate what the matrices would be for 5 by 5, okay, by choosing L as 2, and you can go up and up. You could have a 7 by 7, a 9 by 9, 11 by 11, always odd. Using this overlap integral, using the spherical harmonics, the Y LM, you always get an odd numbered sized matrix, equivalent matrix. Okay. Now, if you go, say, L is 2, so you'll have a 5 by 5 matrix, then calculating what Lx and Ly are, the matrix representations of those operators, Lx hat and Ly hat, more complicated, involves more math, more calculus, right? And the matrices that you'll get for Lx, Ly